Now, the question is, well, H 0, if I plot mod H 0, right. So, at DC clearly it is 1, right. At Fs it is 8 by pi square, at 2 Fs it is 4 by pi square and so on. So, the question is what happens in the middle, right. So, for example, what is h of j 2 pi Fs plus delta f, where delta f is much smaller than Fs, right. So, we change the frequency from Fs a little bit, right, the input frequency, what do you think will happen to the output? And to do that, well, there is I am not going to get into the details now, but I am just going to give you a rough idea of the of how to proceed and intuition about. We already have seen that if the input frequency is not exactly Fs, then each capacitor is going to see different sections of the input waveform over that quarter period, and therefore, the magnitude of the voltage across the capacitor is going to be much smaller than what it would have been if the input is an integral multiple of Fs, right. So, you should expect the magnitude to fall off, right, if you deviate from Fs. So, basically you should expect behavior something like this. Right, there is some kind of qualitative behavior that you should expect. To be quantitative, of course, we need to do a little bit of analysis. And to do that, we are going to, let us say we excite the input with e to the j 2 pi into Fs plus delta f times t, all right. So, when phi 1 is on, right, see, remember what comment can you, when delta f was 0, in other words, when the input was e to the j 2 pi Fs times t, that is both cos or sine, right. What did we see for the voltage across this capacitor? This was simply DC, right. It is it is not changing very much during that the period when the switch is turned on. Now, what do you think will happen if instead of the input being Fs, the frequency changes slightly to Fs plus delta f? Exactly, right. So, what when the input was exactly at a frequency Fs, this voltage would remain constant from cycle to cycle, right. So, in steady state, what you would see here, it would, it would be in this cycle it would be some waveform, in the next cycle it would be exactly the same waveform, and intuitively that is because you can think of it as the following: this input frequency at Fs, right, is being switched at Fs. Switching is basically, in other words, this current, right, we are sampling or multiplying it with a square wave at Fs. So, what is going into the capacitor is the low frequency component, which happens to be DC, correct, okay. And at the same time, the capacitor is trying to discharge through the resistor, which is connected only for a fraction of the period. So, when the two effects basically equal each other, you will have an equilibrium voltage, right. Whatever voltage results is a result of the equilibrium between two opposing effects. One is the mixed down version of the current flowing through the high frequency current flowing through RS, right, and the other one is the loss of voltage of charge from the capacitor due to this periodic connection with RS. Now, so basically if I think of this as e to the j 2 pi Fs into t, right. So, this is Vi, and we can think of this as being multiplied by phi 1 of t, right. So, when we do this, you are only getting these currents. And so on. So, I will draw only one period, right. So, this is so this is so this divided, so the voltage divided by RS is, if the capacitor voltage is constant during a clock phase, the RF current going in through the resistor is simply e to the j 2 pi Fs t divided by RS, that gets multiplied by this waveform, right, and consequently you can see that this is getting, I mean the waveform of the current going through the capacitor is something like this, right, and what do you call this on average is the capacitor is simply averaging this, correct, and therefore, there is some voltage established. So, we are interested in the low frequency component of this waveform multiplied by the width of the phi 1 pulse, correct. So, now by the same token, if the input was e to the j 2 pi Fs plus delta F times t, the current is the voltage divided by Rs, right, and we are interested in figuring out what the low frequency component of this multiplied by this phi 1 of t is, right. Phi 1 of t is basically 1 for Ts by 4 and 0 otherwise. So, as this can be expressed as a Fourier series. So, A sub L e to the j 2 pi L Fs times t, correct. So, what will be the component of this current at delta F? Which component, I mean, what do we need to, which component of the Fourier series? We are interested in the low frequency component of the product, right, but the input is at e to the j 2 pi Fs plus delta F. We are interested in the delta F component. So, we have to worry about which series coefficient here. We need to worry about in A minus 1 e to the minus j 2 pi Fs times t, right. Yeah, when this gets, this will, I mean, so the RF current will get multiplied by the minus Fs term in that Fourier series and will yield, the result is A minus 1 by Rs e to the j 2 pi delta f times.
That one we can think like that we are sampling with that input signal, and whatever fs plus delta f will be there, it will alias as a DC component.
Correct. If the input was exactly fs, then it will alias as a DC component.
And delta f will be DC plus fs.
Exactly. Right. So so you can think of this therefore as the equivalent low frequency current that's flowing into the capacitor, right. So this is A minus 1 by Rs e to the j 2 pi delta f times t, and this is the capacitor. But how is the capacitor is also losing charge. How is it losing charge? When the switch is turned on, the voltage across the capacitor is tending to go down because it's going to get discharged through Rs, right. So what is the but this Rs is only there for 1 by nth of the period. So this is equivalent to having a resistor which is n times larger all the time, correct, because if per cycle, right, it's only on for a small period, and yeah. So if you you want to represent it as a fixed resistor, as far as the low frequency current is concerned, you can think of it as having a resistor which is n times larger, but is on for the entire duration, correct. So this will therefore give us the amplitude. I mean, so if you take this current and pass it through this impedance, you will be able to get the low frequency component of the voltage across the capacitor, right. So sanity check. What is the sanity check? Delta f is 0, right. So what do you think will be the voltage here? So A minus 1 by Rs times nRs is the voltage across the, let me call that Vc1, right. Okay. And what is A minus 1? A minus 1 is the minus 1th Fourier series coefficient of this phi 1 pulse, right, and that is to do that, well, we use standard results from Fourier transform stuff. Remember, if you have a periodic waveform, let us call this P of t, right. That is the waveform within one period, correct. And what is P of t, or in our case, so P of t is simply sum over L A sub L e to the j 2 pi L f s times t. And what is A L? How do you find A L from P of t? It is nothing but integral 1 over T s P of t, very good, e to the minus j 2 pi L f s times t dt, correct. And recall, however, that integral 0 to infinity or minus infinity to infinity P of t e to the minus j 2 pi f t dt is nothing but this is nothing but the Fourier transform of P of t. All right. So, to get A sub L, all that you need to do is do 1 over T s P of, evaluate the Fourier transform of that one period of the waveform at L times F s, right. So, in our case P of t is basically 1 for a duration T s by 4, and therefore, P of f is nothing but it is a rectangular pulse. The Fourier transform of a rectangular pulse happens to be T s by 4 sinc f T s by 4. That would be the Fourier transform of a pulse centered at the origin, right, but this is now moved a little bit to the right. So, this will be e to the minus j 2 pi f T s by 8, because if the origin was here, then it would be just the sinc. Now, it is moved to the right by the pulse is moved to the right by T s by 8, and this is what you get. Now, therefore, A minus 1 therefore is 1 over T s times P of minus F s, which is 1/4 sinc of minus 1/4, right, times e to the j 2 pi f s times T s is simply 1. So, 2 pi by 8. So, that becomes pi by 4, right, which therefore must be 1/4. Sinc is an even function. So, that is basically sine pi by 4 divided by sine divided by pi by 4, all right, and times e to the j pi by 4. So, so in our case this n is 4. So, V c 1 therefore is A minus 1, which happens to be it's n, which is 4 times that is this is, I will simplify this. So, this and this goes away, and therefore, you have 1 by pi root 2 times e to the j pi by 4. I hope there is no error. Okay, seems okay. So, V c 1 therefore will be 4 into 1 by pi root 2 times e to the j pi by 4, right, which is nothing but what is e to the j pi by 4? 1 by root 2 plus j by root 2. So, this is nothing but 4 by pi root 2 times 1 by root 2 plus j by root 2, which is nothing but 2 by pi plus j 2 by pi, correct, and this is consistent with when we put cos in that the first capacitor would have 2 by pi. When we put sine, the first capacitor would have, when we put cos or sine, right? What would be, if we put cos 2 pi Fs times t, what would be the voltage here? What would be the voltage across this capacitor if this was if this was a, well, if that was Fs? It would average the first quarter of the clock period of the input period, that would be 2 by pi. Similarly, when you put sine also, you would average this thing, and that's indeed therefore is consistent with what we derived earlier. Okay. So, all that I want to show here now is that as delta f, so sanity check, this is fine. So, as delta f increases, what comment can you make about VC1? It basically will be A minus 1 by Rs times the impedance of this RC network, which is NRS by 1 plus J 2 pi delta f times NRS times C. Does it make sense? So, this is simply an input current. So, this is the magnitude of the input current. At delta f, and this is nothing but current flowing into an RC network, right? Okay. And so, therefore, the voltage across the amplitude of the voltage developed across the capacitor at delta f will be given by this expression, right, which is a minus 1 times in our case n is 4 that's because of the 4 paths that we have, right. And so, the what is this telling us? It's, I mean, this is telling us stuff that we know already, namely if delta f is 0, then you get the maximum voltage, right. As delta f deviates from 0, what comment can you make about the magnitude of this? It decreases, correct. And within quotes, what is the bandwidth that you can, I mean, for what delta f will the amplitude reduce by a factor of root 2? Yeah, yeah, exactly. So, basically this is n is 4. So, the bandwidth is basically 4 Rs times C, right, times, I mean, 2 pi of course. So, what this is looking like, so H 0 of J 2 pi f basically at Fs has a gain of 8 by pi square, and as you deviate, this is the delta f, this is Fs plus delta f. What happens? As you deviate from Fs, the magnitude of the voltage across the capacitors keeps falling, which then means that the voltage at this node also keeps falling, right, because the voltage at this node is simply, we are taking the voltages across each one of those capacitors and putting them all together, right. So, the bandwidth basically happens to be 4 Rs times C times 2 pi, and intuitively this makes sense because around that center frequency it looks like a low pass filter, okay, with the C of course is the capacitance, and the reason why we have 4 Rs is that Rs is only being connected to the capacitor, yeah, for only 1/4 of the time, right. So, to summarize, therefore, the n path filter or the 4 path filter behaves like a band pass filter. Center frequency is Fs, right? Bandwidth is 2 pi times 4 Rs times C. Okay. There are, and so therefore, center frequency is accurately controlled by the switching frequency, and the bandwidth is accurately controlled by the RC product, right. So, this now allows us to have a wide programmability. Unfortunately, there are also multiple pass bands, right. So, where are these pass bands? At 0, at Fs, 2 Fs, and so on. Okay. And there is also translation of frequencies. For example, H sub minus 4 of 5 Fs, right. Remember, if you put 5 Fs also, you will, I mean, the capacitor voltages will basically have some non-zero averages, right. And when you go and compute the real part of H of j 2 pi f and imaginary part of H of j 2 pi f, you will get a periodic waveform, right, at with a period of Ts by 4. So, basically if you put an input at 5 Fs and H minus 4 is not going to be 0. Remember, only what is 0? H1, let me write that down before we go here, right. H1 plus minus 1, H plus minus 2, H plus minus 3 are all 0. And why are they all 0? Because this is due to 4 path operation, right. Okay, but H minus 4 is non-zero, right. That means input at 5 Fs, right, yeah, will get down converted through H minus 4 of j 2 pi into 5 Fs and yield output at 5 Fs minus 4 Fs, which is Fs. Okay. Similarly, an input at minus 3 Fs, correct, will go through H plus 4 of j 2 pi times 3 Fs and yield an output at minus 3 Fs plus 4fs, which is fs, right. So, not only are there multiple pass bands, there is also potential for out of band frequencies folding, I mean frequency translation, but we knew this already, right. This is an LPTV network, this is exactly what we signed up for. The hope is that it is, I mean, so if you want to prevent this, what do you suggest we should do? So, in other words, we want to filter something around fs, and we want to have a narrow band filter around whose center frequency is at fs, and so we build this thing, correct. But unfortunately, and around fs it obviously does a good job, because it seems to be rejecting stuff from it only lets frequencies close to fs pass through. As you keep going farther and farther away from fs, you will start to see problems. I mean, it is attenuating signals farther away from fs, right. However, at if the input frequency is very far away, so if it is say at 3 fs or minus 3 fs, right, or if it is at 5 fs, basically the LPTV nature of the system seems to be causing frequency translation from these frequencies to fs, right. So, we are at this point, we will be confused as to whether the output at fs is genuinely our filtered input, which is at fs, or it is some extraneous tone which is at either 5 fs or minus 3 fs or whatever, which is getting translated, right. So, this is however an easier problem to fix, and how will you do this? Well, you say here is my four path filter, right. So, this is a LPTV, of course, right, and which is the nearest input frequency that can appear at the output? 3 fs, right. I mean, so basically if you look at the distance to fs, it is 3 fs. So, what you could do, for instance, is to put a gentle band pass filter which rejects 3 fs. So, for instance, so let us say you have a gentle band pass filter. So, this is fs. So, LTI gentle band pass filter, and so this is 3 fs, and therefore at 5 fs it will be even smaller. So, to reject 3 fs and high. Okay. So, this is easy to do because it is very gentle and it only has to reject something which is very, very far away from fs, right. The biggest challenge with band pass filtering is that if you have two tones which are closely spaced, it is very difficult to reject one and pass the other, right. This the N path filter based band pass filter basically is good at filtering close tones which are very close to each other, but it has this problem because of the inherent time varying nature of the network, that it causes stuff to fold from multiple frequencies to output, right. So, this is one way of solving the problem. So, this is equivalently a very narrow band programmable filter. Right, and the programming of the center frequency is very accurate, because the center frequency depends on the switching frequency. If you change the switching frequency, the center frequency of the band pass filter will also change, right. So, so with this I will stop our our discussion on n-path techniques, right. So, we have seen 3 applications of n-path principles. The first is time interleaved sampling, right. The second we saw was multi-phase DC-DC conversion. Third is n-path filtering. Okay. So, in the next class, we will see how one can make when we talked about time invariant networks, after figuring out how to write the matrices and so on and analyze the network, we talked about reciprocity and interreciprocity. We will do the same thing for periodically time varying networks in the next class.